Hello and welcome back to Calculus 2, section 9.2, properties of power series. So last time we learned about power series. I talked about, in the beginning of that lesson, I said we have a sequence, AN, which was the ordered list of numbers. And that behaves more as a number. And then we have series of AN, which was the series was the sum of a sequence, and that is preferably infinite because we want the finite ones are not fun because you have finite amount of numbers to add, it always converges. So the infinite one, and we learned 10 different tests to discover convergence, divergence, and all of that good stuff. And then, with all those operations, within the operation of addition, in a series we introduced finally an x, a variable, and we created a power series which behaves more as a function because we have this x. And these were the three creatures that these are the three creatures that we are considering in chapters 8 and 9. Now, looking at these power series, I told you that there are other flavors of power series, such as Fourier series, which contains sines and cosines instead of x to the k. There are Lorentz series and a bunch of other series out there that are learned sometimes later in mathematics if you are interested in learning mathematics. Now, I also mentioned very briefly that power series convergence doesn't only depend on the shape of the power series, but it also depends on the value of x. By simply altering x, you can make power series converge or diverge. So, the goal of today's lecture is to learn the properties of power series and also look at the convergence of power series. And we're going to start our talk about these properties at the at that level. So consider the power series where all ck's are equal to 1. So you have ck, which is the coefficients, right? And that could be anything, could be any kind of sequence that we learned in chapter 8. But let's say this is just a sequence of all ones. So you see that times x to the k, right? So now, if you consider series 0 to infinity of ck, which is 1, so now all you're going to have is x to the k. Now you should know what this is from your previous chapter. What is it? It's power series, not p series. It's geometric. It's geometric. So now, well, it could be p series actually. Could be p series. So if you are considering this, right, I will say, looks like geometric series. Now, geometric series was that arc business, right? Now, let's not worry about A. So you just have this x to the k mimics r to the k. So now you don't get to say that this particular power series converges or diverges, because it does both. It converges for all x's between -1 and 1, and it diverges for all x's larger or equal than 1, which is to say x less than -1 and x larger than +1. So if you're familiar with the Schrodinger's cat, this is actually the Schrodinger's cat right there. You don't know if this is going to converge or diverge until you know what x is. Do you know Schrodinger's cat experiment?
The cat is either dead or alive.
The cat is both dead and alive until you open up the box and do the measurement, i.e. look at it, right? So there's your Schrodinger's cat in our example here. This power series both converges and diverges until you tell me what x you're picking. You pick x to be 1/2, well, it becomes a geometric series and it converges because r is between -1 and 1. You pick k to be 7, well, it diverges, right? So as you can see, both states are possible right now until you pick an x. As soon as you pick an x, this function, this power series collapses onto either a convergent or a divergent series. Now I get to do this with every single power series under the sun. Because, remember, your series did not have x. Your power series have an x. As soon as I replace that x with a number, power series becomes the regular series, and then one of the 10 tests apply. But then we want to just look at the general case of a power series. And if I'm looking at the general case of a power series, I want to make this converge and diverge arguments looking at the power series rather than looking at every single possible case. So what we came up with is interval and radius of convergence. And those two relate to the values of x that will make the power series convergent. Remember, power series converges into power series converts into regular series which converge or diverge by whatever of the 10 tests you can master. Now, generally, you know that I never do the textbook examples because the textbook examples are there for you to read and you know all the letters and numbers and then you can just look at it. But in this particular lecture, the examples they picked are fundamental and they're awesome. And they show the 3 flavors of types of convergence that you guys can run into. So I actually, in this particular case, explain those. And then we take a look at further examples from homework. But these examples are so good that I actually stick with those. So I'm going to say interval and radius of convergence.
Oh God.
Yes.
Oh God.
Yes.
Is that the reset the whole computer?
No.
Yeah.
It's been a long day.
I know. 3 final exams. I mean 3 cases. 3 cases to learn about interval and radius of convergence. Three cases, 3 examples, 3 problems, whatever. Number 1. Summation x to the k over k factorial from 0 to infinity. This is case number 1. So what happens here is you have a power series, and you see that there is k factorial on the bottom. So you have exponential on top, factorial in denominator. By the growth rate, right, you can kind of assume that the whole thing converges, right? But then I can plug in values for this x, not just 1 and 7. What's going on in infinity? So we have to actually have to carefully analyze these cases. So this is what I'm going to do. I'm going to look at the convergence of the entire power series without considering separate x's. I'm going to look at the convergence of the entire power series by using a ratio test and just dragging this x around and working with it. So use ratio test. Limit k goes to infinity. We know that we are supposed to put the absolute values there. Now, these are the problems that if you don't put absolute values, you're going to get them wrong. I warned you last time we learned about ratio test that those are not there for decoration, and I told you will see why. Now is the time to see why. So you must use absolute values there. All right, so what do we have? We are supposed to go with k plus 1 and then divide by the original series, which means multiply it by the flip. So I'm skipping a step over here, right? Instead of writing divided by x to the k over k factorial and making it to a double fraction, I immediately multiply reciprocal. Now we know what we need to do. We need to peel, right? Don't forget to copy this limit every single time. It's -1 per step. So I know. It's -1 per step for forgetting the limit. So in a problem that has 11 steps, you get -1 for the problem, even if you solve it correctly. All right, peel off. So x times x to the k over k plus 1 times k factorial. So this is when we peel off times k factorial over x to the k. X to the k, x to the k, k factorial, all dies. And we are left with the limit k goes to infinity of absolute value of x over k plus 1. Now, the variable in the eyes of the limit is what? K. We are taking the limit in respect to k. So what that means in regard to x? What's x? It's a constant. In the eyes of the limit, x is a constant that you get to copy. So I'm going to actually kick this x outside of the limit and focus on the limit of 1 over k plus 1. Now, what is the limit of 1 over k plus 1? 0. Very good. So we get x, absolute value x times 0. And what do you get?
0 is less than 1.
0. Okay, so what? If 0 is less than 1, what does that have to do with it? Nice. 0 is less than 1, which implies convergence. Now, in this case, we say that power series converges for all x, and that is what we are. So power series, yep, power series summation of x to the k over k factorial 0 to infinity converges for all x. Now we know that x is on the real line between negative infinity and infinity, so interval of convergence is negative infinity to infinity. And the radius of convergence is half of that. Just put infinity, sorry. Now this will be, these two parts will be clearer with the next two examples. But I hope that you understand now that what we got here is 0. 0 is always less than 1, and by ratio test, when you have less than 1, it's convergence. So we showed, this was a proof actually, we showed that this particular power series converges for any value of x you pick. And that should be common sense because it's divided by factorial, which is superior in terms of the growth. Who had the... good. Problem number 2, case number 2. Summation 0 to infinity of negative 1 to the k, x minus 2 to the k, over 4 to the k. Now I'm going to tell you again, it's a ratio test. As soon as you use the ratio test, you will have the absolute value, which is going to kill the negative 1 term completely, right? Because it's absolute value of negative 1 is 1, and absolute value of 1 is 1. So if they're all 1s, it's just, right? It's going to be 1 all the time. So you're basically focusing on this part here.
You only plus 1. So it'll be like k plus 1, right?
Yes. Ratio test is designed as the next term, which is plus 1.
Crap.
Is that just a sign to, no, listen, you can't take it the wrong way. Thanks.
All right, let's take a look at this problem together since you requested. I mean, I'm supposed to show all of this, but then you were a little bit vicious, so let's go. In this problem, I'm going to, again, always use a ratio test. Guys, sometimes you can use a root test, and you can see over here that you can actually use root test. Root test is also okay to be used in these cases, but then we're not going to use the root test. Let's just use ratio and call it a standard, all right? So what do I have? I have by ratio limit. I guess I'll have to restart because if this is gonna keep happening. Limit k goes to infinity, absolute value. I'm not going to bother to put the negative 1 to the k because all of those terms, because of the absolute value, become 1. So I have x minus 2 k plus 1 divided by 4 to the k times 4 to the k divided by x minus 2 to the k. And it keeps...
What do you say that you don't have to worry about the minus 1?
This one.
Yeah, why not?
Absolute value. Right, this string
okay.
of negative 1, it's 1, negative 1, 1, negative 1, 1, negative 1, right?
Okay.
And when you apply absolute value, they all become 1, and you multiply, nothing changes.
Okay.
Right now we do peeling. So we have x minus 2, and then x minus 2 to the k, over 4 times 4 to the k. So you peel 1, that plus 1, times 4 to the k over x minus 2 to the k. A lot of stuff cancels, no coughing, and we got into the limit k goes to infinity of absolute value x minus 2 divided by 4. There's no k. Very good.
So that means that x minus 2 will be a constant.
Yeah.
But it has an x.
So we are left with x minus 2 over 4 in absolute value.
Even if that.
Now what?
What are we looking for? Aha. So here, I'll write it in blood here. We are looking for convergence. Right? We are looking for convergence. That means that you are going to put less than 1. You want to find for which x's the whole thing converges. Which means whatever is left over here needs to be less than 1. Right? Because this is the step after the limit. Limit is solved. That better be between minus 1 and 1 if we are to see sorry, between 0 and 1 if we are to see convergence by ratio test. So we have now elementary algebra inequality to solve. We have to solve x minus 2 over 4 less than 1, which in elementary algebra we get to write as negative 1 less than x minus 2 over 4 less than 1. Multiply everywhere by 4 to get negative 4 less than x minus 2 less than 4. And add 2 to all of these to get x alone. And look, we found the interval of convergence. Any x you pick between negative 2 and 6, your power series will turn into a regular series which converges. If you pick an x value outside of this interval, the power series will turn into a series which diverges. Do we get that? So what you have here, negative 2, 6, is the interval of convergence. That's what it is, negative 2 to 6. So give me any number between these two numbers.
5.
5. You take number 5, go back to the original problem, replace this x by 5. 5 minus 2 is 3. So you have 3 to the k. And go and you do whatever test you can master from chapter 8. You see, by replacing x with 5, you collapse your power series to a regular chapter 8 series. And you have 10 tests there. Whatever test you can use, geometric, telescoping, whatever, integral, you would see that that number 5 you pick, right, will lead to convergent series. Now, guys, between negative 2 and 6, there are infinitely many numbers that you can pick. All of them lead to a convergent series if those numbers are placed for x. If you use negative 2 or less, or 6 and more, any number of those you replace for your x, the series you get is going to be divergent. Again, whatever other test you try, it has to give you divergent. Now, what's the radius of convergence? So we have the interval of convergence. That's this puppy over here, right? Negative 2 to 6. You can also leave it in this form, whatever.
5.
Now, what's the radius of convergence? Yes, which is?
4.
Very good, 4.
Half of the what?
Well, if you look at the number line,
Yeah.
you are going from negative 2 to 6.
Yep.
So what's in the what's the length of this? Well, there's a 0 somewhere, right? So you have 2 units here and 6 units there, so that's 8 units long.
Oh.
So radius would be half of that 8, which is 4.
Gotcha. That makes sense.
Of course, math. So radius of convergence is 4. Radius of convergence is 4.
This isn't that long.
Let's make one final connection here. Where is this series centered at?
What do you mean center? It's numbers?
Yeah, number-wise. Where is it centered at? It's 2, right?
Oh, right.
Why is it centered at 2? Oh, minus 2 plus. That's the one I was looking for. Who said that? Yes. Very good, man. Why is it centered at 2? Because that's how we define the power series. There's your final ultimate check. Guys, if that minus 2 in parentheses, that is the center of your series, right there. We said centered at, it's x minus a. I believe we did that right there. Look at that. Do you all see it? Word centered. That was 9.1. And it was in the first 5 minutes of me talking about power series. And we talked about what its centered means. It shifts left, it shifts to the right, depending what you need, so that you can have better approximations of functions, right? So now, what's happening is when you go to the next one, over here, we have all of these things click together. We see that the power series is centered at 2 because it's x minus 2. But then if you draw the graph for radius of convergence, we came up that the interval of convergence is -2 to 6. And what is in the dead center of -2 and 6? It's 2. And then you have 4 units one way and 4 units the other way for... So here is the center of 2 with the 4 units this way and 4 units that way. So now you can see on one graph, these graphs are not required, but they're really good for understanding what the hell is going on. The series is centered here because we had x minus 2 to begin with, but then we also see that that's exactly in the middle between the radius interval of convergence with the radius of convergence going each way. Now, you might say, why is this called the radius of convergence? There is no circle here? Exactly. There is no circle here because these are the real series. Lorentz series will have the radius of convergence because the complex plane, it's a disk. So it is a radius. This is just a real axis of Lorentz series. So we still keep the word of radius. But we still have it. What happened? Did it work? It is. Okay, good. Just want to check if it works. So, did this make sense?
Yeah.
All of it? So, as soon as you see the power series, if it just has x to the k, centered at 0. If it has x minus 7, centered at 7. If it's x plus 1, centered at -1. Very well. And then all of these pillars support each other. You see whether the answer is right or not. You know it has to be centered at 2. You go through all the calculation. You come up with this. You come up with radius. When you draw, you have to be able to take 6 minus 4 and get where the whole thing is centered. All right. Case number 3.
Oh, wait.
Yes. Math is funny, I know.
Those 3 parts, that's like the answer, right? That's what you want, all 3 parts of it?
Well, this is the same. So one or the other.
Okay.
When you get the value of x, it was -1 minus x minus 2 over 4 minus 1. Why do you move the 4 to both sides instead of 1? Right there. Yeah.
Over here? Well, this is what we call a 3-sided inequality. So you have to do the same thing on all 3 sides. So we need to get x alone, which means times 4, all 3 sides, and then plus 2, all 3 sides, to get x alone. Case 3, summation of k factorial x to the k, no coughing, from 1 to infinity. Same business. We have limit. K goes to infinity, absolute value. K plus 1 factorial x to the k plus 1 divided by k factorial x to the k. which is the limit k goes to infinity. And now we peel off, so we get k plus 1. Yes? Do not call my name in vain. On k factorial, x to the k, divided by k factorial x to the k. We have k factorials gone, x to the k is gone, limit k goes to infinity of k plus 1 over, sorry, no, there's no over, it's just k plus 1 times x in absolute values, and what is this equal to?
0.
Separate absolute x times the limit of k plus 1 as k goes to infinity. So now you're looking at this and you say, well, that's infinity on the other end, right?
The other side's 0.
So this whole thing over here is infinity.
That's infinity. Infinity plus 1 is infinity with x.
Aha! So now we see that the only chance when this is to be less than 1 is if x is equal to 0. Because, first of all, you get the concept of the limit. When things go to infinity, they are not infinity. Infinity is not a number. Infinity is a concept, mathematical construct. It's not a number. So, when you are thinking about this, this over here goes to infinity. If this is 0, any number that it's going to infinity gets knocked out by 0. Every single one. Whatever this is, and then you say the next number, and the next number, and the next number, they all go 0, 0, 0, 0, because x is 0. If x is anything else but 0, you get infinity and it's divergent. You can't make it less than 1 for convergence. So what happens here is we are getting a convergence of a power series at only one value of x at 0. So this one over here converges for x equals 0 only. Now that means that my interval of convergence is a single point, convergence, so interval of convergence, single point, x equals 0, and radius, obviously, of convergence is equal to 0 because everything happens at this one point. So we had 3 cases here. And those 3 cases were infinite radius of convergence, which means power series converges regardless of what you pick for x. Then we had the next second case where so for the second case we had the situation where we have a finite interval of convergence. It was from -2 to 6. Radius was 4. And now we have this single point convergence. Converges only for x equals 0. And any other value you pick for x, it's going to be divergent. Now what I want to do here is get you to look at the growth rates. Exponential divided by the factorial. Factorial is winning, the whole thing goes to 0, so we have a chance of convergence there. Example number 2. Exponential over exponential. They're of the same weight, right? If they're the same weight, then some ratio of things kicks in, right? And we see that we have our radius of convergence shrink. It's not infinite. And then over here, there's no division at all. Multiplied. Exponential times the factorial. So of course it's going to diverge. But then we can pick 0 for x. As soon as you pick 0 for x here, you put 0 there, 0 to the k remains 0, and then whatever factorial you're picking, that 0 is knocking it out, and we're getting 0 plus 0 plus 0 plus 0, and it converges to 0 in a sum. Did this make sense?
Yeah.
Somewhat? So let's do another example. This is now from the homework. I mean from the textbook. If I hit your homework problem, then just pick something else. And we have a few properties and we're done. So what should we... Hold on. We have to do the problem first. Let's go with problem 18. Summation of -1 to the k of x to the k over 5 to the k, and the series, it doesn't matter, goes from 0 to infinity, 1 to infinity, whatever. 1 to infinity, doesn't matter. All right, go.
This is why I was laughing.
Oh, you evil. Yes.
Because of the
Absolute value, we don't worry about it.
But what if it's like 2 over here? Instead, what is always -1?
Well, nice one.
Is always -1?
The alternating, right? I mean, you could make it, but then why? There's no need.
Every time, same day. This one's really busted out.
It's maximizing the floor.
Oh. You need to write it down. Yeah. You want to see it? Yeah, I'll show you. I got all these.
Right, I guess you're all done. What's the answer? Negative 5 and 5? Oh, I like that. Negative 5 to 5 and the radius of 5? She's not messing around, that's why.
I don't know what to do for maybe one time.
Nothing.
Really?
See, if you paid attention, you would know exactly. Alright, so I'm going to do the peeling right away as well. So now I skipped even I skipped like 3 steps.
How do you like just know what to do?
Always remember my status. Divine. So this gives us x over 5 in absolute values. We are setting this less than 1 because we want convergence. We demand convergence. So that's us setting it less than 1, and then we deal with the inequality that remains behind, which is this one times 5 everywhere, right? 3-sided. So negative 5 less than x less than 5. Perfect. So that's our interval of convergence, and R is 5.
Wow. I was using it well,
now,
ooh.
No U's here.
Wouldn't the R be half of 5? Oh no, no. Yeah.
Now we also see that the final check over here would be 5 minus 5 is 0, so my original series better be centered at 0, and it is. Do you see that?
Yeah.
That's a little check there that you can use. So 0 is exactly in the middle of this interval, which means that the power series is centered at the number that is in the middle of the interval. Or you can go the endpoint minus the radius, or the endpoint plus the radius, whatever. They all have to give you the same answer. So middle of the interval is 0, 5 minus 5 is 0, negative 5 plus 5 is 0, and you have x minus 0 on top. So they all click. And we know the problem is okay. Now, when you told me the answer, right, I didn't go through calculations and solve anything. All I heard was from negative 5 to 5. And I liked it right away because the center of the series was at 0, right? If you told me -2 to 7, I would not hesitate to say wrong, because the center would not be at 0. And I see over here that the power series is centered at 0. So all of this obviously will sink in once you guys do the more example. Would you like one more of these? That's one more.
Yes, please.
Would you like something more diabolical?
Yeah.
Excellent. We all like that. Since Diego asked something very interesting, I want to make him happy because his happiness is also my primary concern in the class. So, by popular demand, I watch him walk home now. -2 to the k, I found one, of x plus 3 to the k divided by 3 to the k plus 1. Whatever, 0 to infinity. Yeah. All right, so I have to help you with this -2k business. You can't ignore it now. When it's -1, you get to ignore it because the absolute value does what? -1 is 1 and 1 is 1 times 1, so nothing happens. Guys, let's use a little bit of algebra over here. So, -2 to the k is the same as -1 times 2 to the k, and then we have -1 to the k times 2 to the k using the rule from algebra, right? Basic algebra rule. So you get to rewrite this problem using the basic algebra by simply writing -2 as -1 times 2, and then each one of the factors gets its own exponent k. So now this problem becomes easier. This was one of the standard, while I was teaching at NGIT, this was one of the standard exam problems. Something like this with a -2 to the k or something. So you get, do I?
7.
Is that a hint? At NGIT, yes. Good. I had no clue that you are looking to retake the class, but that's fine.
So I think I just sold the whole thing and showed you. I know exactly what you're talking about.
Let's spray some water at his face for me, please. I'll do it for you. What? Doesn't look very comfortable. No. I played Counter-Strike when you have like level 25, 511. Oh, no, you're taking I wonder if
Oh, let's go.
put it somewhere, I don't want to put it anywhere. Then you do trouble with them. One second. That's funny.
All right. So this problem is just messy. It is. It has a lot of these parts, but it's the same as pretty much anything else. So we know we ignored -1 to the k. 2 to the k would be 2 to the k plus 1, and then we peel off 1. And then we have x plus 3, and we peel off 1, right? Divided by. Now look, we have to start over here with 3 times 3 to the k. So when we peel 1, it's 9 times 3 to the k. Is that bueno? Do we all understand this part?
Yeah.
And that is the original state, is 3 times 3 to the k. When I make this 3 to the k plus 1, another 3 drops in front. 3 times 3 is 9. Green? Good. Times the flip of the original. Peel off. Divided by 2 to the k. X plus 3 to the k. Done. 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 There we go. Yes, if I can get my colors. So what do we have left? Yes.
Where do you get that?
Limit
Oh, yeah.
of 2x plus 3 divided by 3
K plus 3.
k goes to infinity. There are no k's, which means this is just 2/3 times x plus 3, and we set this less than 1 because we want convergence. So now we are solving -1 less than 2/3 x plus 3 less than 1 times 3 across the board. Divide by 2 across the board. Minus 3 across the board. So minus 3, that's I'll write it and then we'll calculate. So now 3 times 2 is 6, so 9/2 less than x less than -3/2. Do we see the center at -3? Right? Do we see the center at -3? So our interval of convergence is -9/2, -3/2. And then the radius is, when we add the 2, we get 12 divided by 2 is at 6, right? Over 2. 6/2 is, so -3. So center is at -3. And if you draw this, you have -3 is the center. You have -9/2 on this side and -3/2 this way. So the radius is 3/2. All of the other problems are done the same way. I will encourage you to test out the root test as well. Root test might be faster on some of these problems, especially when they are all raised to k everywhere. This problem, everything is raised to k except the 3 that you can just have as the nth root of 3, no one cares. Alright, so now let's talk about the rest of the properties of power series. So we already know about the convergence of power series, and we know it can converge from -infinity to infinity. It can converge on a particular interval, x1 to x2, or it can converge at a single point. We had that case where it converged at 0. Now we want to combine power series. This is important. Obviously, it comes up in differential equations. I already showed you those situations when you combine power series. So, the ways we combine power series. So, suppose that summation of ck x to the k, which is a power series, converges to f of x, and summation of dk x to the k converges to g of x. So we have two power series that converge to these functions. You know what this means. If I give you 1 plus x squared over 2 plus x cubed over 6 plus ... you get to write summation of 1 over k factorial times x to the k, and then you say, oh, that's e to the x, because you know these things. So when I say that some power series converges to f, that means that there is whatever power series you get, you can write it in the summation form, and it converges to some kind of a function. We've seen power series for ln, we've seen it for sine and cosine and e. There are power series for everything else. So, suppose that we have these two power series which can converge to functions f of x and g of x. So, number one, sum and the difference. Now, I'm going to actually write this a little bit more expanded than what they have. I'm going to say summation ck x to the k plus minus summation dk x to the k is equal to summation ck plus minus dk x to the k is equal f of x plus g of x. Now, what does this mean? Well, it means that we can actually take the two sums and put them under a single sum. Now, this is done a lot in chapter 3 of differential equations. I showed you this last time where we did these types of calculations. Here is the example. That's a bad example because there's more stuff to be done. What's up with all these evil examples? Great. Here is the rule which I just wrote at work in differential equation problem that you just do for homework, like that, and on a test, same thing. This is the exam on Thursday. They have this. Look, power series, x to the n, x to the k, whatever, with some kind of block coefficient over here. It starts at 0, to infinity, and over here has n plus 1, so we peel off that 1x, which we kick out, doesn't matter. You see that they actually combine into a single power series right here. And I circled stuff. If they all start with the same counter, which is the purple stuff, and they all have the same exponent over here, they combine into a single power series underneath. Right? So this is one line where these two power series, using the rule that I just gave you, combine into this power series. Now what do you see? This is your CK, and this is your DK. So here's your CK plus DK, because there's a plus there. If there's a minus here, then it's a minus there. I have a whole bunch of these. Where's the Thanksgiving review? There we go. Whole bunch of these examples. There it is. Same thing happening. Starts at 0, starts at 0, starts at 0. Aha! Look at this one. Subtraction. Told you can add or subtract. So here we go. You see this puppy here? It's right there. That's your CK minus 2 is your DK, and then you can have as many of these as you want. You can train 50,000 if you need to. So the rule that you are seeing right now as a, purple thing for me to write is actually going to be used in your differential equation to combine power series into a single power series so you can actually solve the problem. You're going to use this stuff. The next one is multiplication by a power. There was that one case where we kicked the x out or bring the x in, make the n plus 1 power. So the next rule, multiplication by a power yeah.
Is it fx plus or minus gx?
Yes, minus. Plus minus. It has to be plus minus everywhere because he preserves the sign. Anything. So if I have x to the m in front of a power series ck x to the k, I can bring this one inside as ck x to the k times x to the m, and then we know that the exponents, right, just add, so k plus m.
That's m, right?
M. So you can use this rule either way. Sometimes you need to kick stuff outside of the series, and sometimes you need to bring stuff inside. Again, the differential equation problem will dictate which one you have to use. All right. So I will give example of these. Just need to write the third one. Composition. So if age of x is given as b x to the m, where m is positive integer, then power series ck, and then age of x to the k converges to f of age of x. Now, rule number 3, which out of all 3 rules now looks the craziest and the most complex, is the only one that you are actually going to use in Calc 2. The first 2 rules you are going to use in your differential equations. So now let me do the very basic examples of these 3 rules. So number 1, if I have a summation of n x to the n, and then I add to that summation of n plus 2 x to the n, and they both start at 0 to infinity, the result is 0 to infinity, and then I have my n plus 2 x to the n. Now you might ask yourself, why does this work? Well, remember what this stuff is. This stuff is simply a whole bunch of terms that are added to another sum of bunch of terms. Now, what's happening here is that for, well, actually, let's start this one at 1. Start at 1. So now, if you think about this, right, you have x, right, and then 2x squared plus 3x cubed plus 4x to the 4th. So that's the first terms. And then we have output plus dot dot dot, and then big plus. And then the second one, when I start at 1, I have 3x plus 4x squared plus 5x cubed plus 6x to the 4th plus dot dot dot. Now you see that I can get this term and this term together, they're like, and then this term and this term together, and they're like. and then this term, right, and so on. Now, when you take these two terms together, you get 1 plus 3, which is 4, but over here, 1 plus 3 is 4. And this thing as well. So you can expand all of these and show that this actually works the way it should. Matt?
I was just curious if you could manipulate the sigma. Say, for instance, one started at 0 and then one started at 1. Could you just do the first one at 0 and then add it from 1? You know what I'm saying?
What you do is you peel off a term to start at the same location.
That's how it goes.
Yes.
Okay.
Number 2. So number 2 is, let's say you have x squared times the summation of some kind of ck x to the k from 0 to infinity. Well, the variable is k, which means that the whole term x squared is just a constant, because the summation operates on k's. In the eyes of the series, k is the variable, x is a constant. So I can just bring this inside of the sum. Technically what I'm doing is I'm distributing this x squared over every single term of the infinity of terms that are there by bringing it in. So it becomes summation 0 to infinity ck x to the k times x squared. And now just by using algebra, right, we get k plus 2. In some cases, in differential equations, you will have to pull the x out to match to certain things. So if you have summation of ck x to the n plus 1, k plus 1. Well, in this case, it's summation ck x times x to the k, and this x is a constant. There are no k's associated with this guy at all. Kick it outside. And then number 3 is function composition. Well, function composition, the easiest way to understand the function composition, which we are going to use, by the way, in 9.4 a lot, is, let's say, e to the x squared. What is that equal to? Well, we know that e to the x is summation of 1 over, well, we can do immediately x. So x to the k over k factorial, right? From 0 to infinity. Now that expands into 1 plus k squared over 2 plus dot dot dot. To get e to the x to the squared, all I need to do is to replace each one of the no, these are x's, not k's. No one is saying anything. Right? So all I need to do now is to replace each x by x squared. And then simplify it. So function composition within power series allows me to create these complex functions. They're not complex variable, but more complicated, right? And look what we did. We took something that cannot be integrated, turned it into a polynomial, and then we can integrate that like this. That's a 10.4. So we are going to use this idea of composite functions. 9.4. 9.4, yes, thank you. 9.4. So 9.4 we're going to use the rule number 3 to create composite functions and then turn those into polynomials and then integrate and differentiate and do all these kind of things like this, because it's easy on a polynomial. Well, the differentiating and integrating power series, which is in this section, I leave for 9.4, because 9.4, working with power series, is the entire section on differentiating and integrating within power series. So I leave that concept for that one anyway. So we're done. Wednesday, we are going to finish chapter 9, and then by what you guys voted, we are having exam 3, fortunately, on Wednesday the following week, which is Wednesday of what? 6th. So December 6th is, you just remember 18, right? 12 plus 6. So December 6th is the exam. Your quizzes will start on Thursday this week. Your quizzes for the exam. Keep working on those. I just hope that you solved at least 2 or 3 problems on the project. And if any one of you has completed one project with formatting and stuff, I would gladly take a look at it and butcher it. So you can score a lot of points or when you actually submit the project. And I already seen a glimpse of one project. No steps, guys, for calculation. It should look like physics textbook. We talked about it. So whole bunch of text and then occasional number and occasional formula. So I will see you all in 2 days. Ciao.